We'll continue in this video with problem number 2. And for the rest of this, we'll just have several more of these word problems to get a little more practice in setting up our right triangles, seeing what information is given and what it is that we're looking to find. So in problem number 2, we have a 42-foot tall tree. It's casting a shadow that's 23.5 feet long. To the nearest whole degree, what is the angle of elevation from the tip of the shadow to the top of the tree? So once again, a lot of information. Let's get our picture drawn. If you go through the problems in the book, you will see some of them start you with a picture and then the description, and others, just like these problems, just give you the word problem and you have to draw. We should be able to handle both. The problems that give us the picture is certainly a nice little, little boost for us, but we should be able to handle without. And, little things I should have pointed out in this one. You could have little differences that the building and the person is on this side of the building, but we still need the right triangle for reference. So just if we draw a picture, but we have little differences, like I said, maybe you put the person on this side of the building. When I draw my tree, does your shadow go this way? Does it go that way? Those are tiny little differences, but when we have our setup, sides, angles should all be in the appropriate spots so that we could see the right triangle and again, find whatever it is that we need. So I'll do this one a little reverse. So here's my tree. And again, notice I'm not much of an artist and you don't need to be. Even though up here I drew my building, just a little rectangle. Here, does it really matter if it's really tree shaped? Just something so you know, there's your tree. The tree is 42 feet tall. Shadow, again, this time I'll let the shadow go this way away from the tree. Easily could go the other way. The shadow is 23.5 feet long. Now, what are we looking for? We're looking to the nearest whole degree. Well, there's two things. First, make sure your calculator is in degree mode. And to the nearest whole degree, more rounding directions. So at the end, we know how far to round. But what are we looking for? Well, we're looking for an angle. But which angle? The angle of elevation from the tip of the shadow to the top of the tree. So kind of like what we saw in this picture, there's no actual line here, but we drew that in to see the right triangle, and that same thing is happening here. Let's connect the tip of the shadow to the top of the tree. That is the angle of inclination that we are looking for. And notice the subtle differences. Going back to problem number 1, we had one side, wanted a different side, had the angle. In this problem, we've got two sides, but now this time we want the angle. But in any of these types of problems, that's always going to be the scenario, that there's always going to be at least two things given and one thing wanted. In this problem, now you do have these two sides of the triangle. So if you use Pythagorean theorem, you could get this side, but that's not what you're asking for. That might lead to some alternative solutions, but it's certainly going to be a longer solution because we can get this directly right now. Once again, to the nearest whole degree, what is the angle of elevation? So basically, essentially, we're looking for theta. Well, what do we have from theta's perspective? Oh, another little thing, right? Again, those little assumptions. Trees don't always grow perfectly straight, but we're essentially treating this like a right angle. Again, just like so many other word problems in math, these little assumptions that we do take. So again, there's my right angle. And from the theta's perspective, we have the opposite and the adjacent. So tangent is the trig function that we're going to want to use. But as we use this again, up here when we plug that in, again, they're not all tangent. That's just a coincidence for these first two. But here again, still set up that relationship. Some people are just happy to skip right to the actual work that they need. So same thing here. Some people want to start here establishing everything they have and what they want. But now they specifically plug in. The opposite is 42. The adjacent is 23.5. Solving for theta this time. Up here, we just solved it like a regular equation. Looking for the unknown, the x, the question mark, a little direct solution. But here, remember, now we're looking for theta. So this is where we talk about the inverse trig. So inverse tangent of 42 divided by 23.5. Again, I can do that all at once. This time I'll show you on my scientific instead of the graphing calculator, but still can do it all at once. Second tangent. Again, I can't say it enough. If you're using the calculator, it should almost always be a quick check. No matter what, you have the angle, you want the angle, are you in the correct mode? Such a common place that people make mistakes. Sometimes, these are word problems, so sometimes things can make sense. We can, think about something like this, the tall building, looking at that big angle, it makes sense, that's a big side. So there is some reason you could use, but again, still a lot of easy little mistakes happen just because people aren't in the correct mode on their calculator. So inverse tangent of 42 divided by 23.5. 60.7, again, to the nearest whole degree. So 60.7 would round up to 61 degrees. And again, we said in the previous video, make sure you're paying attention to the directions. Sometimes for an angle, they want the nearest whole degree. Sometimes they want the nearest tenth of a degree. So you get 60.8. The nearest hundredth, 60.77. The nearest thousandth, you get 60.772. So again, just always make sure you're rounding appropriately. That's, I mentioned a lot of little mistakes that do come up, but that's a second one. People do all the right work, but again, they just don't pay attention to the rounding directions and they lose a silly point at the end of the problem. So just to be careful with that. Okay, let's continue. Let's still keep going. Let's get some more practice with these word problems. So let's move into problem number 3. This time, we're looking at a plane flying 1,000 feet above the ground. And, sorry, I had to stick this in. I just went a little offline here. So the plane is 1,000 feet above the ground, and the angle of declination from the airplane to the runway is 23 degrees. What is the distance from the plane to the runway? Oops, and I forgot. Let me put my rounding directions. Let's round to the nearest tenth of a foot. Sometimes, like above, we saw the rounding directions were right in the middle of the problem. Sometimes they like to include that at the end of the word problem. Either way, just to handle it and to, again, at the end of the problem, when we get our answer, make sure we round appropriately to what it tells us. Up here, we round to the nearest whole foot. Now we're going to go to the nearest tenth of a foot. So once again, let's get our picture. So I'm going to put there's my airplane flying 1,000 feet above the ground. There we go. Now the next part, the angle of declination. That's a little bit stranger to most people. For a lot of times when you've seen a couple of problems, we talk about the angle of elevation. Well, elevating from what? We're always elevating from ground level. So when we talked about the angle of elevation from the shadow to the top of the shadow to the tree formed that angle. Up here, we had the angle of elevation to the top of the building, but we went from the ground to the top of the building. In this one, you need to start off with something straight. So when we talk about the angle of declination, we have to start off with a straight line away from the plane, and then the angle going down from that to the runway. So the runway would be right here. So the angle of declination from the airplane to the runway, now we're looking at this angle is 23 degrees. Okay, we still have a right angle. A little fact, if you don't know, when we ever talk about something above ground, what measurement are we talking about? It's always directly above ground. So that gives us our right angle here. And what are we looking for here? The distance from the plane to the runway. We are looking for this side over here. So, where do we go from here? Well, a couple of little things, and there's going to be two very quick alternatives right off the bat in this problem. Because the issue with problem number 3 compared to problem number 1 is that here, when we naturally took the angle given in the problem, it was already inside the right triangle. So inside the triangle, we had an angle, we had one side, we wanted another. But in this problem, It's like, okay, we know this side, we want this side, but we don't have any angles inside the triangle. So what do we do from here? Well, there's two possibilities. Some people, this is where a little bit of geometry comes in. And again, that's why we did cover some of these basics, like the sum of the angles inside any triangle is 180 degrees. We're going to use that principle on something else here. So, option number one, some people remember some facts about lines crossing through parallel lines. We have these alternate interior angles, and there's a lot of geometry facts that point out that these are the same angle. So that's something that people remember. Well, if this is 23 degrees here, then the angle of elevation from the one ray to the plane would also be 23 degrees. So like I said, that's a whole, remember this, two parallel lines, a line cuts through, well then we know that this angle is the same as this angle. This angle is the same as this angle. There are lots of other things we could do, that this angle is the same as this angle. Lots of other ways we can cut through that, but that's one way. And now, this angle, you have the opposite side. You want the hypotenuse, we would set up sine. Sine of theta is opposite over hypotenuse. So sine of 23 degrees would be 1,000 over blank. So that's one perfectly good way to set this up. But there is, again, an alternative, and it comes up here. That this, I've got the plane in the way, so let me kind of ignore the plane for a moment so we really see the top corner of the triangle. And realize that if we have this situation, there's another right angle up here, so that these two angles, the formal term is that they are complementary. That these two angles combine to equal a right angle. These two measures add up to 90 degrees. So that means if you have 23 degrees up here, that would leave you with 67 degrees right here. I'm just doing 90 minus 23. So again, these two combine to give you a 90-degree angle. If you know this one is 23, 90 minus the 23 gives you 67. So if this is the angle you put into your triangle, well, from this angle's perspective, this is the opposite and this is the adjacent. So this would be, you have the adjacent, still want the hypotenuse, so now you would use cosine, because cosine uses those two sides, and you would get cosine of 67, and cosine of 67 would be 1,000 over the blank. And now to finish solving either one of these, again, come back up here. I don't want you to just try to memorize, well, this should always be tangent, this should be sine, this should be cosine. You should be able to draw or look at the picture and determine each problem individually based on, again, angle you know, side you want, all putting those three pieces together. But now the second part is that when people solve this one, because the unknown was in the top, as soon as you cross multiplied, you were done, you put that in your calculator and that's it. But in this one, or this one, you cross multiply blank times sine 23, put a variable in if you want, x times sine 23 equals 1 times 1,000, you're not done. You have to finish solving for your question mark, and you would do that by dividing. In this one, it would be the sine 23. Here, it would go question mark times cosine of 67. So you'd have to divide the cosine 67. And this is another spot where those cofunction identities should make it clear that no matter which way you're doing this, and remember, you don't have to do both. It's just trying to show you that somebody sees it this way and you'll get a correct solution. Somebody else sees it this way. You don't have to do both. Either one is fine. But just remembering that with the cofunction identity, we would get the same thing either way. And I'll show you that. 1,000 divided by, again, I'm already in degree mode. And again, to the nearest tenth of a foot. So we would get, we are 2,559.3 feet away. And same thing if I did it the other way. 1,000 divided by cosine of 67, and we get the exact same answer. So any of these problems, letting my calculator do the heavy computation, do it all at once, because again, if you start doing multiple steps, if right here you start saying like, okay, well, sine of 23 is this, you're not going to copy all the decimal places. So therefore, you're going to round off. And then you divide that over, and you're doing 1,000 divided by a rounded off number. So when you go to round off again, you've now double rounded. So it's best thing, we only round once, and the best way to do that is to just do all your arithmetic at once, so you get an answer, and you just make sure you're rounding to the correct spot, to the nearest tenth of a foot. That's why I looked at the 100th spot, which was a 0, and just rounded off right here. Okay, let's just do one more. Again, some people, it's like these word problems. You can look at these different situations with planes or helicopters. There's a good example in the book where people are trying to measure the distance across a river. So they just, instead of trying to cross and measure, they walk down the side of the river and then take an angle measurement. A lot of different situations where you can end up with a right triangle. So again, we have several good examples here, but you definitely want to make sure you're getting good practice, also doing the examples in the book, in the homework. But now let's wrap up this unit with this fourth problem. Now we've got a 25-foot ladder placed against the wall. How far should the base of the ladder be away from the wall to have an angle of inclination of 20 degrees? And once again, directions at the end, and once again, we'll round to the nearest tenth of a foot. So let's get my setup. And again, I'm kind of tend to make my right triangles in these problems in this direction. It doesn't matter. It doesn't matter which way you orient your right triangle. It's about getting things in the right spot. So what do we have? We have a ladder against the wall. There's the wall. Here's the ground. We assume that the wall and the ground have a right angle in between them. And there's my ladder. My ladder is 25 feet long, so that in this problem ends up being the hypotenuse. So now again, just quickly going back, look at the three different problems. Started with this one. This distance went here, we wanted this distance. This one was actually about an angle. In this one, we knew this distance and wanted the hypotenuse. Again, this is not a guessing game. We don't just randomly place these values wherever we feel like. We're always reading the problem to make it accurate. So it's just so easy when people set these things up that they just, again, they kind of go into autopilot and they just kind of plug numbers in anywhere. And again, at least you're on the right track, but we want to be more specific. The 25 feet clearly has to go here because this is the ladder in the picture. Okay, how far should the base of the ladder be away from the wall? There's the base of the ladder, there's the wall. We're looking for this distance. Well, what else do we need to know? If we want to know this value, they have to have some more information. Well, we want the angle of inclination to be 20 degrees. So the angle of inclination from the wall, from the floor to the ladder, we want that to be 20 degrees. So now we want to find this side. Okay, pretty good setup. Nothing too terrible. I mean, I should point out, this was a nicer problem in that the 20 degrees was already inside the triangle, so we are ready to go. But I can certainly point out, plenty of people, well, once you know this is 20, you equally know this is 70. So those are little things people can do, and it's certainly not as bad as, like I said, back in number 2, people who do Pythagorean theorem to get the hypotenuse, that's pointless. That really doesn't help at all because you're not getting to the answer that you're looking for. You're just adding extra work. And that's kind of similar here, but people put the 70 in and then they get more options with which trig function can they use. But again, we shouldn't need to do that. We have everything we need. From this angle's perspective, this is the adjacent, this is the hypotenuse. So we're back to cosine. We had cosine as an alternative in number 3 after we did a little extra maneuvering. But in this one, with this setup, that's exactly what we should be using. So cosine of 20 is going to be blank over 25. I didn't pick to put the unknown in the numerator here. That's the way it worked. It was the adjacent side, so that's what went into the numerator, and the 25 was the hypotenuse. So again, I didn't pick that this is the relationship, but now that that is the relationship, this one happens to be a little bit easier because I just cross multiply and I'm already solved for my question mark. So now again, rounding to the nearest tenth of a foot, we are doing 25 times cosine of 20. Oh, notice everybody, if you just put a number next to a trig function, your calculator knows. Just like right here, you don't need a time sign. You can, but it's not necessary. The calculator knows that's multiplication. So to the nearest tenth, we will get 23.49 becomes 23.5 feet.